x of omega sub k equals the sum from n equals 0 to capital N minus 1 of x of t sub n times e to the minus j omega sub k t sub n. So that's the DFT.
Can we turn the brightness down or something?
Oh, look at that. What's going on there?
Oh, it's back. That's good.
This is new.
It's better that way.
What?
It's better that way.
It's better. Yeah, there's an AGC. I wonder what it was keying on. It may depend on what's nearby, or maybe it depends on how much of the screen is covered. I don't know. Well, let's just watch it. Yeah, it's normally automatic. All right, so that's the DFT formula. The same thing is up there, although somebody went up there and erased the minus sign. Somebody from physics or something like that. You know, because different communities have different conventions. It doesn't matter, you know. Actually, you know, if you erase the minus sign and then replace it by I, that's a cool thing to do. Because it turns out that the same people who use I instead of J tend to use plus instead of minus. So you can get really far translating different communities back and forth by just thinking I equals minus J. So it's just one way to speed up the conversion. But it's in signal processing, the minus sign is there in the forward transform, and then it's not there in the inverse. So let's look at the inverse DFT. So to get back to the signal, little x of t sub n equals 1 over n, which is an asymmetry, times the sum over bends, the sum over the bend indices. So the sample numbers in the frequency domain are called bends. In the time domain, they're called samples. But they're both samples. They're both sample numbers. So now we're summing over the spectrum x of omega sub k times e to the plus j omega sub k t sub n. And so if you get rid of the minus going in the forward transform, then you have to put it in the inverse transform, which they did. So that's okay. Yeah, I don't know who had this opinion, but they should have at least changed I to J. Let's see. So that's the forward DFT and its inverse, and so they're strikingly similar, and they really are, you know, the same sort of thing. One of the things we'll see is that you can see this as a rotation. So that matrix, the FFT matrix or DFT matrix, which you can get as the Fourier transform of the identity matrix, that turns out to be orthogonal, not orthonormal. So it's got, you know, if you square it, so to speak, you know, the Hermitian transpose of it times itself is not the identity, but n squared times the identity. So it's unnormalized, basically. Now you can normalize it, and if you normalize it, then it is an orthonormal transform. And actually, I should clarify that an orthogonal matrix is normally defined as orthonormal. When you study orthogonal matrices, actually, to really get precise here, I shouldn't call it orthogonal, I should call it unitary. So, you know, a unitary matrix, this is just a little linear algebra size, just terms. So unitary is when the matrix A, Hermitian transpose times itself, is the identity, and then orthogonal is this is for a real matrix. Maybe I'll make it a B. B transpose B is the identity B real. And I would like to say that this is the orthonormal case, because we need to distinguish between orthogonal and orthonormal. Because you can be orthogonal without being normalized in the case of the inner product and in these linear transforms. So it's just a terminology point. All right, so unitary is really the right term for a complex matrix that is self-adjoint, just to throw out another term. So the matrix Hermitian transpose times itself is the identity. And that's the property of the normalized DFT matrix. And so what do you have to do? Let's call it S tilde. S tilde is just defined as 1 over the square root of n times S. And and then you have the property you want. Let's see. Yeah. Because then the DFT, the DFT will be normalized if you have this square root of n in it. So let me just say that over here, if I put a 1 over square root of n in the forward transform, then I'm left with a 1 over square root of n in the inverse DFT, and we can associate that square root of n as a normalization on the kernel. So it's a sum of x, samples of x times this complex sinusoid. We're going to study complex sinusoids divided by square root of n, and that makes it unit norm. And you can see that by just summing the magnitude squared. There's capital N of them. When you take the magnitude squared, square root of n becomes n, and you sum n of them, and you get 1. That's just normalization. Okay? All right, but this is the standard definition because you don't always have to normalize, and you don't want to spend the time taking a square root and doing a divide in signal processing. Signal processing is usually a real-time, high-speed, optimized situation. It tends to happen in very, very small chips. Nowadays, very, very small segments of small chips. And you want to not waste hardware. You don't want to do any operations that are unnecessary. And so, you don't usually see the normalization. Even if it's an inverse FFT, you'll just let it run unnormalized. So you'll save your normalization for the very last stage when you really have to do it. But mathematically, we want to be able to invert it, and so we use the 1 over n in the definition of the inverse DFT. So now we're supposed to know everything about this in the terms of the pieces of it. We're about to embark on really making signals and exponentials, and we're going to prove Euler's identity. And maybe I'll just write down Euler's identity because that's really the only other piece. So we've been introduced to the DFT, the inverse DFT, and Euler's identity. And Euler's identity is simply e to the j theta equals cosine theta plus j sine theta. And it was just stated without proof for this section. And we're supposed to be able to manipulate it because we understand how to manipulate exponents and complex numbers. And this led to the polar form of a complex number. So if you just multiply 3 by r, you can represent any complex number as its radius times e to the j angle. And then that breaks out into the Cartesian coordinates as r cosine theta for the x plus j times r sine theta for the y. So that gives us our polar form for the complex number. So with Euler's identity, we can do this. And next time, we'll at least spend some time proving it. We'll derive it. And that will actually derive E. So what is E? I mean, I just wrote down E. What is E? Well, E is 2.71828. It's kind of an amazing number. It has 1828 in it twice. So you can remember 10 digits of E by just remembering the year 1828. Does anybody know anything that happened in 1828 that'll help us? Andrew Jackson. Andrew Jackson was elected president in 1828. Well, if you're on a desert island and you need 10 digits of E, it's easier to do this than evaluate the series.
Is
Now,
also when Beethoven dies?
what?
Beethoven dies in 1828?
Is that right? Beethoven died in 1828? I did not know that. I knew that.
Something around that.
Yeah. Ah, darn. Well, that gives you 9 digits of E. So, or just remember Beethoven's death plus 1. It's like.
That was 1773.
Oh, really?
No,
No. He was alive in 18.
He died in 1828.
Yeah. Okay. All right. So.
close.
Big years in our history. So, but the actual definition of it is it's a limit. So it's the limit as n goes to infinity of the expression 1 plus 1 over n to the n. And this we will derive next week. So we will invent E. In the process of trying to prove Euler's identity, E will fall out as just part of the derivation. And so you can always reconstruct it. All right, so now these are the elements. And what can you do with Euler's identity? Well, there's a number of cool things. One of the things is to set theta equal pi. And then you have e to the j pi. We know that equals minus 1, right? You can just plug it into Euler's identity. It's cosine of pi, which is minus 1, and then sine of pi is 0. So if you rearrange that slightly, you get what some people will call the most beautiful formula in mathematics. And its beauty stems from the fact that it has exactly one instance of 0, 1, j, I. I should probably really use I now. I, pi, and e. It's got one addition. It's got one multiplication. It's got one exponentiation. So it is, one of everything related in a non-obvious way. So it's just a really beautiful, amazing thing involving fundamental constants and operations. So let's play with Euler's identity. We're supposed to be able to play with it now and get results with it. So let's say, for example, what if I say, give me cosine of theta plus j sine theta to the nth power? Do you know how to do that? Yeah, the de Moivre theorem, right. So you basically really want to go to polar form. What? Bless you. Yep. Yeah. Concert tonight will be cold. Take a blanket. So now, if you go to polar form, then it's e to the j theta to the n, e to the j n theta, and then go back and you get de Moivre's theorem, cosine n theta plus j sine n theta. And what's also cool about this is that n does not have to be an integer, right? There's nothing about this that requires an integer. So it's a very general relationship just handed to you by Euler's identity. Just to remind you, so we all know what a complex number conjugation is. So you just negate the imaginary part, and in polar form, it is a negation of the phase or the angle.
Can you say a little bit more about that? That's very unintuitive for me.
Why the conjugation would do that?
Yeah.
Well, let's say it's defined as this, okay? So then, and then we say equal maybe to that, all right? And then we apply Euler's identity, and we get r cosine of minus theta plus r or j r sine of minus theta. And one thing you have to know about sine and cosine is that sine is even, cosine is even and sine is odd. So that means that cosine of minus theta equals cosine of theta, and sine of minus theta equals minus sine of theta. And you can check that, on a side calculation. You can set up a little angle here with the y value, the x value, and so you can see that that if I negate the angle down here, then y will go to minus y, but x will remain x, right? So if you negate the angle, I'll try to write minus theta in there. If you negate the angle, then you've negated the sine. The opposite over the hypotenuse is the sine. The adjacent over the hypotenuse is the cosine. So you can just see it geometrically that sine is odd and cosine is even. And so that proves it. So I can just say, check. So I've just shown analytically that negating the phase corresponds to negating the imaginary part. You can also see it just in looking in the z-plane. Another thing we know about is the complex plane. So you've all seen the complex plane. We're supposed to be comfortable there. And so let me draw an arbitrary point, and that's also expressible as r times e to the j theta, where there's theta. So this is the x-axis, this is the y-axis, and maybe I need a specific x and y here, so r0, theta 0, x0, y0. So if I've defined conjugation as negating the imaginary part, then you can see that flipping from the upper plane to the bottom plane, half plane, corresponds to negating the angle. So it's basically an up-down flip. If you're comfortable with MATLAB notation, flip UD, flip up-down. A flip up-down is equivalent to angle negation for every angle in polar coordinates. Now that's true in this half. What if you're over here? We're saying here. So we have this big angle here, and we negate it. It still comes around and looks for all the world like an up-down flip. So one of the tricks for a complex conjugation is just negate I everywhere it exists, or negate j. Just go into the expression. It's just some big gnarly formula. Just replace every instance of I by minus I, or minus j if you want to do that. And then you have the conjugate. It's just because it's an up-down flip in the complex plane. So you can think of it as just a transformation on the plane. And if you get it in polar form, you can just negate the angle. And then we have relations like this, that the modulus of a complex number is it's by definition r. It's just the length of the complex number. And so that can be written also in terms of the real and imaginary parts. And then we can also write down the angle of a complex number, and that is theta. We define it as the angle in the polar form, and that in Cartesian coordinates you do the arctan. And this is an atan 2, so to speak. If you've done any programming, you know that there's this problem with the quadrant. So you need the y and the x coordinate in order to know what quadrant you're in. You can't have a function of just the ratio. You have to know whether it's a plus over a minus or a minus over a plus. So really, I should not even write this. I should really write this as an ordered pair like we do in software, because you can't just pass the ratio to the arctan and get all possible answers. So that's the kind of stuff we can do. Oh, and here's another one and that we'll use a lot, and that is the definition of sine and cosine in terms of Euler's identity. So let's look at an example. Let me just get one page here. A couple. So we know that e to the j theta equals cosine theta plus j sine theta. And we also know that e to the minus j theta equals cosine theta minus j sine theta. And that's because theta is, cosine is even, sine is odd. So this is just two uses of Euler's identity. Now if we add these, we get that e to the j theta plus e to the minus j theta equals 2 cosine theta. And the sine parts cancel. In other words, cosine theta can be written as e to the j theta plus e to the minus j theta over 2. And the same thing occurs if you subtract. And so if we subtract these two equations, we get e to the j theta minus e to the minus j theta equals, cosines cancel, we get 2j sine theta. And so from that, we find that sine of theta is equal to e to the j theta minus e to the minus j theta over 2j. So these are very valuable identities because it looks like maybe you might think that we've made sine and cosine more complicated by expressing them as complex numbers, not one but two complex numbers. But this is actually showing you how sine and cosine are more complicated because they consist of two complex exponentials. And so what we're going to be doing is making sinusoids. So a sinusoid is essentially just letting theta equal omega t, where omega is frequency in radians per second, and t is time in seconds. So that is how we make a sinusoid, by just letting the angle theta be an omega t thing. And so that means that a sinusoid based on, let's just take one like sine omega t is a sinusoid. It means that that sinusoid can be expressed as two complex sinusoids, e to the j omega t minus e to the minus j omega t over 2j. And so this is where the negative frequencies come from. So I kind of wish I had picked cosine first. Let me do cosine down here. Cosine omega t equals e to the j omega t plus e to the minus j omega t. Am I cut off? All right. Over 2. All right. So I'm going to plot that one. And so this is now an omega axis. And then I'm going to plot the amplitude. I've got an amplitude of 1/2 at omega, and I've got an amplitude of 1/2 at minus omega. So this is how a real sinusoid gives you two components. So what's really fundamental is not cosine omega t, it's e to the j omega t. So the really simple fundamental sinusoid is e to the j omega t. And so this one is 1/2 e to the minus j omega t. So e to the j omega t is the simplest sinusoid. It's the one that gives you a single point of energy in the spectrum. But it's complex. So if you want to make a real signal, you have to add that to its conjugate. So any complex function can be made real by adding it to its conjugate, right? Because it's some function over the complex plane added to the vertical flip of that, and so that's going to cancel the imaginary part every time. So there is the basis of the positive and negative frequencies just coming out of Euler's identity. It just falls right out.
In that bottom equation, the second e is supposed to have a negative exponent, right?
This one here?
Yeah.
What is that?
The second e will have a negative exponent?
Oh, thank you. That minus sign is just missing, wasn't it? Yeah. Yeah, I was missing the minus sign somehow. Right. And now I can try to plot this one as well, but there's this j there, so I sort of need another axis. So you can imagine that I could, for the positive frequency component, I could let it go off in this plane as the positive direction, and then in this plane it would come this way. So you can sort of plot these things that way. Now I need to make sure I'm pointing at the right thing. So that's how far we can get just knowing Euler's identity, just stated without proof.
Question.
Yes?
So is that why, when we took the FFT of the sine in that MATLAB demo, that there were two?
That's exactly right. Because our example was a real sinusoid. It was like a cosine. And so every real signal will turn out to have an equal magnitude at plus frequency and minus frequency. So for every frequency omega, you will have a certain magnitude in the spectrum. And if the signal is real, you'll have exactly the same magnitude at the negative frequency. That's a general fact of real signals. So the only single frequency signal is this guy. This is the only signal that has one frequency and no others. And it's never real unless it's DC, unless the frequency is 0. If the frequency is 0, you have a real sinusoid at frequency 0, but it's just a constant. Every non-zero frequency, it's complex, or if you want to make it real, if you want to make it a pure sinusoid, so to speak, then you've got to use two frequencies. You've got to use plus omega and minus omega. So next week we'll introduce sinusoids in a general way and also exponential decays. And we're overdue for a break, so let that sink in for 10 minutes. Oh, question?
I don't quite follow the diagram, or what it's, I followed everything before the diagram.
Okay. Well, I'm going to make it a little bit cleaner here. So we have cosine omega t equals e to the j omega t. We just proved this using Euler's identity, right? We just summed two instances of Euler's identity
Yes.
and got this formula. So that we can think of as 1/2 e to the j omega t plus 1/2 e to the minus j omega t. And so we interpret this as an amplitude of 1/2 at frequency omega and an amplitude of 1/2 at frequency minus omega. And so now I'm introducing something that I can call a spectral representation. I'm really introducing that because we never made this plot before, all right? And in this plot, I have frequency omega and I have amplitude, okay? And just from looking at this formula, I can say that the amplitude is the coefficient of e to the j omega t. So at frequency omega, and let me make these specific omegas, omega 0. So we got a specific frequency omega sub 0. Then at omega sub 0, I've got an amplitude of 1/2. And at frequency omega minus omega 0, I have an amplitude of 1/2. So it's just a way of plotting the amplitude versus omega in this signal.
So the amplitude is 1/2 for both positive omega sub 0 and negative omega sub 0.
Yes. And we have a problem with sign. It's not so easy, right? Because it's e to the j omega 0 t minus e to the minus j omega 0 t over 2j. So we've got this, j in the denominator. So the amplitude is complex, right? It's 1 over, so j can come upstairs with a minus sign. So I can say it's amplitude minus 1 over 2, minus j over 2 is probably the best way to say that, e to the j omega 0 t. And then the j is going to come upstairs and cancel this minus sign, so then it'll be a plus 1/2, plus j over 2 e to the minus j omega 0 t. So the amplitude here, if we plot it, we have to say that it's, we have to decide how we want to plot it, but at omega 0, you would probably want to have it going down. And what I was suggesting earlier is that we use the orthogonal plane for complex parts. So this would be the j direction, let's say. And so then at minus omega 0, we have amplitude 1/2, or j over 2. Let me go ahead and include the j. And then at plus omega 0, we have the amplitude minus j over 2. So that convention allows me to put them together. So in other words, I can plot sine and cosine simultaneously in this spectral representation plot where amplitude is plotted in the plane orthogonal to the omega axis, and it's a complex plane orthogonal to the omega axis. So you see this kind of plot. This kind of plot is actually used, and it comes up. You'll find it in papers. You'll find it in the book. It's convenient. It's good for analyzing things. It comes up again when we look at Hilbert transforms. This is a good way to pictorially derive the Hilbert transform using this kind of plot. So does that make sense? Now, the one step that I agree you can argue about or ask me about or want more clarification on is, why is the amplitude the coefficient of e to the j omega 0 t? In other words, I'm sort of thereby defining e to the j omega 0 t as the fundamental sinusoidal component, the single point. And so that's true. That is what I'm doing. And that's what falls out of Fourier theory.
How did you get the j to be in the numerator from?
Oh, I used that 1 over j equals minus j. This is just one of the little cliches you get. So if I multiply 3 by j, I get 1 equals minus j squared. J squared is minus 1. So you just get used to taking j out of the denominator and flipping the sign. Now, after the break, I'll show you how to derive this mathematically. In other words, I just basically introduced it, but you can also derive it. And I think it'll be a fun counterbalancing view to see how you really get this answer just doing a Fourier transform of a sine wave and having it pop out. I'll just call it another independent view of the thing, another way of deriving it and where it really came from. Unless you don't want a break. If nobody wants a break, we don't have to take a break. We can leave 10 minutes early.
I want to break.
All right. Take your break. Clear your mind. Have your moment of Zen.
It's fine if you want to turn it in a notebook, but if you're also planning on taking your class notes in the same notebook, that might become problematic. But only because, I mean, you can't always count on me to have this back the next day. Just for future reference. Hey, Jimmy.
Hey, Pablo, how's it going, man? I enjoyed those non-existent birds last night.
I love your pizza. So good.
Oh, thanks. Great to see you, man.
Yeah, same. So I found the fourth hammer
Oh, great. Where was it?
in my locker.
Oh, good.
Yeah.
But a different locker than.
Yeah. 'Cause I used to put it in a different one.
Yeah,
Remember how
yeah.
we used to share it with Esteban? Or with,
Yeah, I see.
Yeah.
I don't remember. Are you talking about a locker that?
No, the fourth hammer.
Oh, was Esteban using it? I didn't know that. I didn't know that.
Yeah.
What was he?
So I was like, yeah, we can keep it in this locker. And I guess when I was just cleaning up, because I used to have those two lockers, I guess I just put it inside my locker.
Mm.
So I thought about it when Jay said, like, no, it's not there. Like, maybe in mine. I'm gonna go for the concert. So it was like,
Excellent.
Now we're going to use my locker, and that's, I told Carl, yeah, let's put it in his office. So, yeah.
Mm-hmm.
So it's ready for more physical models. What do you got in your pockets now? Are you working on something?
Well, here or at Morforte, most of my physical modeling work nowadays is Morforte stuff. Yeah, but
Sounded really good.
you know what? And I didn't even really get a chance to work on the sound. I just ended up using one of Pat's, but it was pretty good. I mean, he had it dialed in pretty well. But I would actually do some EQ. I would take out some of the highs. I would get a little more rounded hollow body feedback. I would have taken off some of the edge off of it.
But like what you're doing is like showing that you can actually use it instead of a guitar to
Even
perform live.
even just a finger on glass can play a guitar. Yeah, but there was a blend of what I'm doing versus what's in the XML. So there's a rigidity there that's not in a live thing. But if you're just trying to lay it down, if you're just trying to get it on a recording, you can really definitely do it. You can really,
Well, I don't think
keep the
you
dimensions.
I don't think you missed a note at all. Or like this.
I didn't miss any notes, but I definitely did one bend that shouldn't have been a bend. So there was a sharp note. But it's good to have at least one point of fail, just to show that you can have that you can actually, that it does matter what you do. So I mean, to some extent, all the music here is just experimental, and it's just ideas, right? We're just throwing out ideas, and
Exactly, yeah. That was great. So then we just switched to like, hardcore, and it was amazing.
yeah, that was the Gina factor when the big stuff came in, right?
It's really good.
Could you hear the dragons pretty well?
Oh, yeah. And the marching, whatever.
The approaching army, right?
Yeah.
And then the battle sounds. And if you listen to that battle, you can hear it's like 1,000 voices if you really listen. It takes a long time to hear it all. I had to hear it. Gina did it. I mean, she's a professional sound engineer, so she's really a pro. Yeah, so this all grew out of a Shanghai conversation. We were, Karma was visiting, and she was being a hostess, being a former student, and she was, showing us all around, and we were all going out to dinner, and I had this project sort of on. It's just one of the many, back shelf, back burner things, and I said, you're the perfect person to ask. How would I synthesize? How would I create a battle sound? I mean, without copyright infringement. Do I actually have to record individual sword clinks